Streams give us a different way of thinking about infinite lists and lazy evaluation. What do I mean by a stream? Well, a stream is a sequence of values, and we can think of them as being processed in a network. Lazy infinite lists we can think of in this way. Values of the list are produced as they are needed. So some simple examples here. You can think, going to the right of the screen, you can think of map as being something that takes a stream of values in, x and y and z, and produces g of x, g of y, g of z. And you can think of iterate fx as being defined recursively to give x, fx, f of x, and so on. Now, one definition for iterate fx is this. It says iterate fx is x colon map f on iterate fx. So you can see that the first element of iterate fx is x, so the first element of map f iterate fx is fx. So you can see that this is going to give us the values that we need. But let's just take a look at how computation with this works in practice. Okay, let's think about what happens when we call iterate plus 1 from 1. That becomes 1 colon map plus 1, and then on iterate plus 1, 1 again. So we call this function again from scratch, and this becomes 1 colon, well, what does iterate plus 1 look like? This becomes map plus 1 on 1 colon iterate map plus 1 on iterate plus 1, 1, and this becomes 1 colon, and then plus 1 on 1 is 2 colon, and then we get a map plus 1 embedded inside another map plus 1 and calling iterate. So you can see as the evaluation proceeds, we get a longer and longer collection of nested applications of map. So this function, if we perform it on a long list, if we iterate, I don't know, the first 1,000 steps or first million steps of a function, could well result in a computation that takes a long time, uses a lot of space, and so on. But there is something from but there is a stream approach to this that allows us to get a much more efficient algorithm. Let's see what that looks like. Well, here we know that iterate fx is a stream, and we're reusing that stream here. So why don't we say iterate fx equals, let's call it out for the output, where out equals map equals x colon map f. And now we don't say iterate fx, we say out again. And then we can see this description as a description of a network. We're saying, what do we do? That our output is x colon so this is our output. It's x colon of map f applied to that output. So instead of recomputing iterate fx from scratch, what we do is we share that stream, we push the output here into map f, and then append x on the front, and values will flow around here. So let's see what happens here. The first value that comes out of here will be x. And so that x will flow through here. It will flow through map f, and so give us fx, and then will come out here, but also go round here, and it will become f of fx. And that will be output, and then it will go round again, and you can see that each time round we add an extra f in front of the result. So this definition of iterate fx, where we explicitly define the output list, the output stream, recursively, is a much more efficient algorithm. And so what we can see here is using recursion, which becomes a feedback loop in a network, we get an efficient implementation of iterate fx, where output is equal to x colon map f on the output. And indeed, we can look at the performance of these two functions. So iterate is defined by the first definition, and we see here that we get, we can take the first 1,000 of iterating plus 1 from 1, and that takes 0.05 a second and about 52 million bytes. Whereas with the network version, with the stream version, we get the result 5 times faster, and we use something like 5% of the storage that we did in the first. So clearly something is going on, quite serious is going on here. If we then take the first 1 million, our stream version gives the result very quickly in still less than 1/10 of a second. It uses chews through a lot of storage, whereas the non-network, the first definition, simply doesn't terminate. I had to interrupt the computation. So you can see here, there is a radical difference between the two that I showed in the hand calculations earlier on. Now, a similar approach allows us to build the partial sums of a list of numbers coming in. So suppose the numbers coming in are x and y and z, the output is x and x plus y and x plus y plus z, and so on. So the input list comes in, we append 0 to the output of zipwidth, and the other input of zipwidth is the output list itself. And as you can see, the output list will be 0, followed by x, and then that x will match with the y coming in, so we get x plus y, and then the x plus y will match the z, so we get an x plus y plus z, and so on. So following the values in those streams, you can see that this will give precisely these partial sums, the sums of the first n elements of the list. You can try that out, for example, by taking 100 on sums of the list 1 dot dot. So thinking of infinite lists as streams can be very fruitful if you can define the function that you want by a network using processors like zipwidth and map and cons and potentially filter, though filter is a bit problematic because it might chew up all the elements in the stream, but certainly you can use filter. So other functions can be used. Now, something like reverse wouldn't work on an infinite list, so you do have to be careful. But functions where you get the first element of the output with the first elements of the inputs, you will work well in a stream approach like this.